lecture or recitation. So, hi. Okay. Let me just, I'm gonna just do this real quick. Okay. So there is one topic I wanted to cover for the first exam. The first exam's in 2 weeks. And there is a topic I wanted to cover that I didn't cover previously. It's a topic that in the past has been found on the exam. So I would like to, I don't know the content of this exam explicitly, so I would like to cover this because it's been useful to students in the past. And the topic is recovery, recrystallization, and close. The false exam's next week. Okay, yeah, it's the 22nd. The false exam's the 22nd. Yeah. Thank you, Tyler. So I think the false exam is the 22nd, which is a week from tomorrow, right? So we have one more recitation on the 21st before this exam. So let's see if there was anything posted by Clive. New test. That's the test of the webcam thing. Okay, that's, yeah. Topics to be examined in the October 22nd exam. Ductile brittle transition, critical resolve shear stress, several force distance curve questions, bonding interference, stress strain curves, several electronic configuration questions, several general dislocation related questions, recovery with crystallization. That's what I want to talk about today is recovery with crystallization, diffusion, home, Rockley rules, planes and directions, vacancies, coordinate numbers, unit cells. That's quite the list. So today I want to talk about recovery, recrystallization, and growth, and then we can transition into other topics if people have any questions or any topics of interest. Okay, cool. Let's get started. So, recovery, recrystallization, and growth is a process that is covered in the lecture slides. I believe it's chapter 6 or chapter 7, and it describes the phenomenon that occurs when we look at how we can control grain size in materials. So we talked about grain size and how it can dictate material properties, right? So grain size can be used to tune yield strength and material strength. The smaller the grain size, the larger, the higher the yield stress. And so grain size is kind of fickle, but recovery, recrystallization, and growth is a way that we can control grain size. So what is it? And so how we get to this process is a processing step that's normally done on very deformed materials. So these are materials with lots of defects in them. These are materials that have experienced a lot of plastic deformation. And so here Okay. So what we have is this is all material cross section, right? And there's a lot of defects in it. So we're going to add a lot of dislocations and your grains, right? Something crazy like this. So a material that has a lot of defects and how it's very deformed, a lot of dislocations, would probably have a very high tensile strength, right? A yield stress that's very high, and a very low ductility. So the ductility is very low and the yield stress is very high because we have all these dislocations. And we may want to change that. I mean, there's many reasons why we would want to evolve this crystal structure for whatever reason. And so one of the few ways we know how to change material properties is to heat it. So we can heat a material and see how the response changes. So that's why at the x-axis here we have temperature. Let's put this a little closer so you can see. What is the word on the y-axis of the graph? Yes, that's a great question. So the y-axis is just property, like it's like anything. So here we have tensile stress and here we have ductility. And so they're not like the same units, but it's important. We're going to see as we increase the temperature how these material properties change. And the other property we could graph would be internal stress. So the y-axis isn't really clearly defined in this way because it's denoting multiple different types of variables. That's a great question. So we have a very deformed structure and we want to modify that in some way. So the first thing we do is we try to heat it up. So initially, if we heat up the sample, so this is room temperature here, we're going to heat it up to some arbitrary value. Maybe I should try a different color. Is that better? Okay, I think that's better. So as we begin to heat up the sample to maybe about 200 degrees Celsius, like that's still very low in terms of metals, right? And so what we will see is we won't see a big change in our ductility. Right? So at this temperature, we don't see a big difference in our material properties. But what we do see is that now these dislocations and localized stressed atoms have more energy so they can move a little bit, right? So when we discussed diffusion, we said temperature drives diffusion, right? So if you give materials more temperature, more energy, they will be able to diffuse better. So at this point, good morning. Good morning. At this point, the materials atoms, they have just enough energy to start moving a little bit. So if you're in a stressed state, you might relax or move slightly to a less stressed state. And so this is called recovery. Where heating the material a little bit does not change the macroscopic properties, but it does allow for the internal stress of the system to decrease. If we continue to heat the material to higher temperatures, right? Maybe we heat it all the way up to 1,000 degrees, what will we see? And what we will see is at these temperatures, this middle range of temperatures, we have atoms being able to diffuse and move long distances. And what's going to begin to happen is that these dislocations will move, and in a very defected structure, atoms will start to diffuse and they will begin to form new grains, right? And these new grains will be formed at the grain boundaries of the old grains, because what will happen is atoms who are in high stress states will diffuse to the grain boundaries, and then they will say, hey, you're in a stress state, I'm in a stress state, this is stupid, why are we like participating in this system, you know, it's dumb, I'm going to form my new grain boundary, I'm going to form my new grains with my friends. And so that's what happens, is we give atoms enough energy to form the new grains. And in doing so, what happens? What happens is the yield stress drops. And the ductility increases. And this is because a very deformed crystal structure has a low ductility. So we're forming new grains, new pristine crystals that aren't as deformed. So the ductility of the overall sample will increase. Likewise, this deformed crystal structure before, it was strain hardened, cold warped, or however we want to call it. So it had a high yield stress. And these new materials, they are, pristine in that way that they don't have a lot of defects. So the yield stress decreases. And so we call this recrystallization. So recovery is the first step, recrystallization is the second step. And the last step we have is if we continue to heat the material, we'll experience grain growth. And during this step, what we see is that the material properties, they don't necessarily change that much, right? They reach a plateau, they reach an ultimate value. So yield stress goes to here and ductility goes up high. But what happens is the grains begin to grow. So at this step, we have the material, the atoms have enough energy, right? The atoms have enough energy to really diffuse and grow. And what results in is that there's a lot of large grains that are of uniform composition. And the idea is that if we do this slow enough, like if we heat up slow enough, then we really produce grains that are large and uniform. And in that way, we produce a material that has a high ductility and a low tensile stress. And so this graph is often accompanied by another graph here. I'm going to erase these things. What we have on the x-axis, we have temperature, and on the y-axis we have grain size. And so during the recovery step, the grain size is non-existent, or it's a very deformed material, right? So the grain, but as soon as we get to the recrystallization step in the middle, we have a very small grain size because we're forming a lot of new grains. And as we continue to heat the material, allow diffusion to occur, we come up with a grain size that increases in this way. So recovery, recrystallization, and growth becomes a very powerful tool or processing technique that we can use to target a specific grain size and a specific tensile stress or ductility. And so typically that is how, when we engineer alloys or engineer metals, that's how we process metals to create a specific grain size and a specific. So what we do is we create the composition or alloy to our liking, and then we deform it a lot. We introduce a lot of defects to the point where it's a little excessive, and then we allow it, we heat it up and allow it to relax, diffuse, form new grains, and we stop that process when we reach grain sizes to our liking to fit specific material properties. So in the past, I can't speak for this year because this year's a little different, because it's going to be a multiple choice and online, but in the past, this graph has always made an appearance, on the exam. So I would hope that everyone appreciates it, and if they have any questions, we can talk about it, of course, but please understand recovery, recrystallization, and growth. At recovery, there is no grain size. Yeah, so so the idea is that in the initially during recovery, like this is a very deformed material, so it's very plastically deformed. And so I think, if I remember correctly, there is a PowerPoint. Let me see if I can. This is actually really cool. It's actually pretty neat. So let me see if I can get it up, the PowerPoint. And maybe these images will help explain it a little bit better. Okay. Cool. Okay, so I want I want the images. Okay, here we go. So initially, here we have a material that is cold walked. So this is actually pretty neat because we see the grain. This is a grain. This is a grain, etc. And all these lines are all the defects in the grain. So these are all the edge dislocations. So it's true that there is a grain size of this material, but it is so defected, it is so deformed that it's not very useful to us, right? This brass sample is so deformed that we can't really be confident that it will perform in the way we want it to perform. So what we do is we heat it up, and in this case, crystals begin to nucleate after 3 seconds at 580 degrees Celsius. So this arrow, I guess, is pointing to a new crystal or whatever. But what we see here is after 4 and 8 seconds, we begin to see all of these new grains form, right? So what happens is previously we have atoms that exist in a very stressed state, and they're like really stressed out. And if you give them enough energy, the ability to move, they will reorganize into these new grains because these new grains are a lower energy state. And we see very quickly how after 8 seconds, right, we form a new like microstructure of all these new grains. So yes, so that was a little bit of a long-winded answer to your question, but like there is a grain size before, however, it isn't it's not the target, so we kind of just ignore it in terms of this graph. So yeah. And then after 15 minutes here, we see these grains become really large, right? After 15 minutes, we see these grains grow in the grain growth region, and these grains become very large. So yes, these images I think are very neat. And then here we have just this graph that I drew, but in a more elegant type of configuration. So this recovery, recrystallization, and growth. Here we have tensile stress. So initially the tensile strength is very high during recovery, and as we nucleate new grains, it drops. And that actually can be a little counterintuitive, right? Because we said that grain size can dictate tensile strength, right? So if you have these very large grains in the beginning, you might want to say, okay, but shouldn't having a lower grain size increase the tensile strength? And in a non-deformed crystal, you are correct. So in a non-deformed crystal, you can say that tensile stress is inversely proportional to grain size. But what we have here is we're going from very deformed crystal to a pristine crystal, right? And in that way, the deformed crystal that's cold walked will always have a higher tensile stress than the pristine system. And that's why our tensile stress decreases as we have these really small grains. Yeah, and so then this process occurs at elevated temperatures for humans, but not so elevated temperatures for metals, right? So we're talking about 600 degrees Celsius, like so 700 degrees Celsius. So these are very hot temperatures for humans, but for metals, they're not, because a metal could have a melting point of 2000 degrees Celsius. So this is still very much a solid processing technique. I don't want to do math right now, so I don't think we're going to do math. But yeah, so that was, what chapter was that? That was chapter 7. So chapter 7 describes that in more detail if you are the type of person who wants a written account of something. So great questions all around. Let's see. Critical resolve shear stress. Have we discussed critical resolve shear stress in recitation? I don't think so. Nope. Yeah, I think so. So we can go over that now, if that works for everyone. Let me just. Oh, I have to. Okay, hold on. Okay. So critical resolve shear stress. It's kind of a big pivot, but it describes the let's see. Yeah. Okay, so in polycrystalline materials, right? So let's back up. So okay. So what we have here is we have a crystal or a schematic of an atom array that has an edge dislocation in it, right? So here is our edge dislocation. It's our extra half plane of atoms in the crystal. We've discussed plastic deformation and how plastic deformation is the movement of dislocations through a crystal. So what happens is if we apply a force like this and from this direction and a force like that from the top, what would happen is these atoms will move to the right, the top atoms will move to the left, and what ends up happening is we break these bonds, pivot these atoms over, and we come up with a system that looks like this. Right? And now we've, okay. And now we've introduced some elongation, right? Right, like so by applying the shear stress, we've shifted these atoms over, we've resolved the dislocation, and we've introduced this extra plane of atoms at the end of the crystal, and that's the plastic deformation. That's the permanent strain on the system, right? So a lot of times you want to be able to do that, but you know, when we look at a metal, we don't know which way the atoms are oriented, right? We can't say the atoms are oriented this way, so I have to apply the force like this. Moreover, when we have polycrystalline materials, it's kind of impossible to really do that because all the crystals are oriented in different directions, you know? So even if you apply the correct stress for one crystal, the second crystal, it might not be the same stress. So when we look at it that way, we have a problem because one stress for one crystal might not be adequate for another. And as a result, that aggregates on a macroscopic scale to this idea of how like, because we have a polycrystalline material, there will always be a crystal that is not perfectly aligned to the stress that we apply. That being said, there are some ways that we can, there are some ways in which we can optimize the force we apply. So okay. So what we have here, this is chapter 7. Like, this describes the same question we're talking about. So we have this crystal that exists, and it has a slip plane and a slip direction, right? So the slip plane is the close packed plane of atoms, and the slip direction is the direction in which the atoms will move when we apply a stress. And so we want to optimize this in some way, but we don't know the orientation. So we can make all these samples, and then we can pull on them at different directions. We can pull on them on different kind of directions to see where's the easiest to break the sample. And what we might find is that, like, we might want to pull uniaxially directly up or directly across. And that is not always, because we might, if we have this rod, we might want to pull exactly up and down or left and right, because that intuitively makes a lot of sense. But what this is showing is that the stress required to move for dislocation movement, or stress required for plastic deformation, the way we optimize it is through this relationship here, where the stress we apply is multiplied by the cosine of the angle lambda and the cosine of the angle phi. And so what it's basically saying is that you have to optimize these two angles between which you apply the stress. So one angle is the direction of the stress and the plane that we're trying to move atoms along in the x, and the other is in the y. And so when you have cosine of a number times cosine of a number, and we're trying to optimize that, the highest is if they are both 45 degrees. So what we find is that the critical resolved shear stress is highest when we're 45 degrees from the plane. And this is seen, but here this is like a pretty famous image of some grass that is deformed in this way, and we can see all of the different planes that have slipped because we applied a stress 45 degrees from the actual sample. Or the slip bands here. So yeah, this is actually pretty cool. So put another way, we don't know the orientation of the crystals within this system. And when we want to induce plastic deformation, we want the atoms to move along a slip plane and in a slip direction. So to optimize this, we have to make and to induce plastic deformation, we have to make sure that the stress we apply is larger than the critical resolved shear stress, which is the stress required to induce plastic deformation in a material. And how we do that is through this relationship in blue here, where we have the material stress we apply, this this value here, and we have these two angles. And so the way to optimize this is just to apply the stress in a 45-degree angle from your material, because we have these two competing forces. And then if you are a math person, there is a mathematical example here. So we apply a stress in the y direction that is 60 degrees and 35 degrees adjacent to the slip direction and the slip plane. So when we plug those values into our equation here, the 45 megapascals times the cosine of the angle between u and the slip direction and the force and the slip plane, we get a value of only 20 megapascals actually applied to the system. So in this way, even though we've applied 45 megapascals to the sample, we haven't been able to surpass the critical resolved shear stress of 20 because we only applied 18.4. So no plastic deformation will occur. So yeah, okay. Let me think. Yeah, so what I would like is that if everyone can review the topics for the first exam, and if you have any specific questions, we can discuss them. That would be really beneficial for me, so that I don't want to devote time to something that everyone already understands. So if you have any questions for next week, please let me know. The list of topics is posted to the class, so that should be a little beneficial for everyone. I will post this lecture. This recitation was recorded, so I will make sure that I give everyone the link for that recording so that they can refer to this if they would like. But I think that's enough for today. Unless anyone has any questions about unless there's any topics people want to broach. You have previously taken his class, or is test difficult? Should we? Yeah, okay, so I haven't taken his class. I didn't go here for undergrad, but I have TA'd the class for 3 years. So this is, and previously, it's always been a written exam. So this is the first year that the exams are online, and I don't really know how that will be different. But what I will say is that in a class like this, there's a lot of volume of material, right? There's a lot of volume of material. So you have to be familiar with all the material, but you can't, just by the nature of all the volume, you can't go as in depth with it, right? So a lot of the questions are designed to prove that you have confronted the material and you're familiar with it, right? But this is an introductory course, so we'll be probing for expertise. So what we want is so that you are familiar with all these ideas and you can prove your competency in understanding them. So I don't think you should expect any math, because this isn't a computational course. This is a conceptual class. So in the past, the first exam has been, people have done well on the first exam. The second exam was a written exam that was all conceptual, like long form answers, and people didn't do as well. And then the third exam was also multiple choice. All the exams cumulative. Yeah, so not explicitly, but kind of. And what I mean by that is that the first exam, they'll ask you about grain sizes and Hall-Petch relationships and Hume-Morphy rules. So you have to understand those basic concepts. The second exam is on metals and steel specifically. And in that way, like, you might not explicitly have to regurgitate the Hume-Morphy rules, but you would have to apply them to the question at post. So I think it's not cumulative in that way, but if you don't understand the concepts of the first exam, you will struggle in the second and third exam. So that's why I'm here and the other TAs are here to hammer out any questions you may have. And really, please, you should bug us. You should ask us questions. You should email us questions. Don't be afraid to annoy us, because you're not annoying us, really. Because that's our job, is to help you. So please let us help you. The class isn't designed to be tricky, right? The class is hard because there's a lot of information, but it's not supposed to be. So it's very straightforward. Would you consider it to be easy? And it's kind of a loaded question. It is straightforward because we give you the information, we give you resources for the information, and we tell you what's going to be on the exam. There's no trick questions. I think I don't want to call it easy, because I feel like that's unfair to people who think that the material is difficult. Because for a lot of people, it can be difficult. So I think it's a different way of thinking, that material science is a different perspective that a lot of people are just confronting for the first time here. So a new way of thinking is always kind of hard. But if you are comfortable with the PowerPoint slides, if you're comfortable with the written text for the textbook, you have all the tools needed to do well. So I hope everyone can do well. But I don't want to call it quote unquote easy. Yeah. And I think for this list of exam questions, I think we have talked about all of them to some degree now. So I hope that none of these topics seem out of left field. So yeah. Please let me know if you want to discuss anything for Wednesday. Because if no one gives me anything to talk about on Wednesday, I'm going to go back to phase diagrams. And phase diagrams are on the second exam. But we need to discuss them. So unless you tell me something, I will say, okay, everyone's good with the material for the first exam, we're going to move on. Okay, cool. So good luck, everyone. Have a great week. Talk to me if you want to talk to me. Okay, so with that, I think we are done for today. All right. Bye-bye.